So my name is Amin. I did my PhD in the Scala team at EPFL, and I was mostly focused on the theory of the type system that underlies Scala, and trying to find a core type system that makes sense in theory and can be used in practice. And so in this talk, I'll just give a retrospective on this, on DOT, which stands for Dependent Object Types. And this is the type system that Martin used as the core type system in the new compiler Dotty. All right, so as we know, Scala fuses ideas from object-oriented and functional programming. And this is something that you can also see in the type system. So if you look at types in Scala, you have almost, you really have almost two dimensions. One which would be the functional dimension, where you have parameterized type, such as list of string, and you can have an existential type where you say you have a list T for some type T that is fixed but not known. And then you can have also a higher kind of type, list, which is not a type in itself, but it's a function from types to types. And on the modular dimension, you have these types that come maybe more from the object-oriented tradition, where you just have the usual nominal named types, such as Scala dot collection dot bitset, and you have this compound type, where in some sense you take the functionality of two different types, such as channel and logged, and just mix them together. And this refined type, where you start with a base type and then add extra functionality. And just to give a few examples, so in any case, type members play an important role in Scala. I mean, they can be used for modularity, like in this cake pattern, where we have a trait symbols that have an abstract type, and then a trait type that has an abstract type symbol. On the other hand, each one of these traits define the other type. So symbols define symbol and types define type. And it's only when we put the cake together that we really tie all these abstract types with one another. And to give another example, which comes from the functional tradition, but which we kind of can also express in Scala using these type members, this example comes from the functional data structure book by Chris Ozaki. And here what you can, this book is usually in ML or in Haskell, but this is how you would do it in Scala. So you could say that you have an abstract type heap, an abstract type LM for the actual underlying elements, and then you can implement this heap module by giving an actual implementation for a heap. So here you would say a heap is a list of node, where node is kind of maintaining some sort of invariant over a structure. And so what then path-dependent types give you is a way that in your program, if you have two different heap modules, then by default, Scala will not allow you to mix and match these abstract type members. It will treat them as separate separate types. And so so this is useful because now, of course, you could have defined this heap module arbitrarily differently from this other heap module in terms of what is the actual definition of this type member. So if we go back to these types in Scala, I mean, one way in which we might try to simplify things is to maybe reduce one of these dimensions to the other. So one idea would be that if we have a class list LM, so just the usual list parameterized by an element type, then maybe you can represent this as a type member LM instead. So as a basically change from a type parameter to a type member. And then list of string becomes a list where you refine the LM type member to be a string. And then what happens to existential type and higher candidate type, where they kind of just both end up being this list, which now has this type LM, which is fully abstract. So something is lost in this reduction, but maybe it's a good basis to try to study a core type system just based on those modular features. And just to emphasize with higher candidate type, in general, what's tricky in these encodings is if you end up doing things where the parameter type kind of disappears, as here if I do type rep of t equals string, or here it kind of just, we lose the structure of having a member. We're just saying rep of t equals t. So these are tricky using these sort of encodings, because we kind of don't have a way to do these function computation at the type level. But for now, what we want to study is really just these type members and these path-dependent types, and kind of have a nice theory around this. And just to give another motivation for where this can be useful, type inference in Scala can be a bit brittle, because sometimes there's no most precise least upper bound. So if you have an if expression, usually what the type inference system will do is that it will try to take the least upper bound of one branch and the other branch. So here it wants to take the least upper bound of C and D, but then there's no type that you can write out that will be perfectly precise for this case, which is a little bit contrived. So this is contrived, but it actually happens in practice, where you might get an error message that has this gigantically long type. And what happens is that, I mean, this is an example that I took from an actual bug report. And here, what happens is that at the end, we don't really care what we're putting in these branches as a value or as a type. But on one hand, we have a mutable set. And on the other hand, we end up, a mutable set. And on the other hand, we end up having a mutable map. And so the Scala type inference is working really hard to try to find what is common between the signature of a mutable set and a mutable map. And so it creates this gigantic, common type. And this is why you can get something like this. And this was noticed because the compilation was going very slowly, just because it was trying to infer this type that it's actually discarding anyways. And in Dotty, one way that this can be simpler is that we can always just rely on using union types when we need to compute a least upper bound, instead of trying to actually eagerly compute what is the least upper bound. Okay, so we want to study foundations, so that first we can ensure properties such as type soundness, ensuring that if you write a reasonable program, and I mean, if you write a program that type checks, then you are guaranteed that certain errors will not happen at runtime. And at the same time, by working on this core calculus, trying to design it such that it sounds, this also feedbacks into the language design as a whole. And I will also show an example where it helps in detecting hidden connections between language features. And finally, it's a formative thing to do, which is why we don't want to necessarily pick an existing foundation, but kind of inspired by what is currently in Scala, try to work out a core type system that is useful. And so the aim, what we're really trying to do, is these sort of type parameterization just through type members and path-dependent types. In that sense, we can do modules from the traditional functional programming literature, because we have these type members, so we can, basically our objects are first-class modules. And we want to have subtyping and objects and classes as well. And I'm saying it's minimal because we don't want to worry about things that are outside of just thinking about types and their relationships. So things like inheritance, mix and composition are out of scope. Maybe there's a way to model these things in the theory as like through encodings or extra work, but we don't want to necessarily have it hard-coded. And so this is what this was the motivation for dependent object types, and it was kind of a pretty long journey to get this working, from the initial vision to an actual calculus that we can prove sound and has nice properties in terms of being uniform and pretty easy to reason about. And so just to give an idea of what we model, so the first thing is that we have these structural member types. So in this calculus, all we have are method members, like this, where you have a method M that takes a parameter X of type S and returns something of type U. And we have a type member, L, which is lower bounded by S and upper bounded by U. And then these type members give rise to these path-dependent types when they're eliminated. So if you have an object that has a type member L, then you can do x.L. And then what we have then is also recursive self-types, so that we can model all the usual object things, and we can also then combine these structural members together using intersections. So I can have multiple members in one type. And here the subtyping lattice is really that we just want to be able to always take the least upper bound and greatest lower bound of two types with the union and the intersection. And what's nice is that this is, I'm just showing you the syntax, but it really also gives you an idea of what you can do, because there's no additional well-formedness rules. It's anything that you can express by combining these different operations is pretty much valid in the system. Okay, so just with these sets of types, we can model type parameters. We can model variance by playing with the lower bound and the upper bound. We can do also nominal typing as well, which is the same idea, playing with a lower bound that is abstract. We can fully abstract. We can then hide the structural aspects of a type. We can do generative modules, self-types, and simple classes as well. And just to give an idea of how we got there, we really explored a landscape of things, starting with the simply typed lambda calculus, and then adding quantification to get system F. And so this is the part where we add the type parameterization, and then also adding translucency to get the lower bounds and the upper bounds, and on another dimension, adding these path-dependent types to get to these systems that are closer to dot. So the difference between, say, system F and these D systems are that in these systems, like system D, we unify type abstraction and term abstraction, and we rely on these type members and path-dependent types to encode the usual type abstraction. And so, yeah, this just gives you an idea of what was the roadmap. So we first started studying how to add these lower bounds, and then how to be able to unify this type abstraction and term abstraction using type members and path-dependent types. Then adding a subtyping lattice, which also introduces some, I mean, depending on how you do these first two steps, adding a subtyping lattice might be more or less easy. Finally, adding records and adding recursion over self. And so just to give an intuition of the rules specifically for path-dependent types, what this says is that if X has a type member L with lower bound S and upper bound U, then we expect that X.L is in between these two types. So S is a subtype of X.L and X.L is a subtype of U. So this is really the intuition for path-dependent types, and it's something that you would use in Scala as well to reason about your program. So here I have, like you can think of, I have just this straight keys with this abstract type member key. And then I implement keys using hash keys where I say type key is equal to int. And now, I can define this map keys generically over any keys, and I rely on this path-dependent type in the return type. Now, if I look at this rule again, and I see the different ways I can abstract this keys signature, what I can say is that, well, I have keys with a type member key, and then that means that I'm completely abstracting away from what is exactly the implementation of type key, or I can make it fully transparent, or I can make it just upper bounded and lower bounded. And just following this rule, I can then know that, well, one can be viewed as a lower bounded dot key because one is an int, and int is a subtype of lower bounded dot key because we have this part here. So you can think of this int as being this S. And vice versa for upper bounded, it goes the other way around. And here, if I inverted lower bounded and upper bounded, then this wouldn't type check. So this rule is fairly intuitive and is useful for thinking about these path-dependent types. But we'll see later that it also is kind of funny because by transitivity, that means that S is a subtype of U. So what if you define a type member where the bounds don't make any sense? In some sense, that means that you're admitting that you're admitting some subtyping relations that were not there by default. So we'll come back to this. Okay, and just to complete the picture, I showed you the types already. What's here on this side, and just to complete it, this is what the term language looks like. It's nothing too surprising for a calculus, for a model. It's really just trying to show that you have these objects, and you have, well, these objects can contain type members. Here they're just aliases, or like method members, and here we give the actual implementation of the method. And then you also have method application, and that's basically it. And we do use a store to keep track of objects, but you don't really, you don't have to do this, but it's useful. Okay, so now the question is, what about semantics and soundness? So what we want to show then is that if our program type checks, we won't get certain kinds of errors. And let's look at what happens in Scala. So here is a very short program that when you run it, it will actually end with a runtime cast exception. And that's a bit strange because we're not using any casts in this program. So what happens is that here we have this function id2, which if you trace what goes on is really just an identity function, but it allows you to convert from anything to nothing. So in some sense, it just allows you to collapse your subtyping lattice. You can convert from anything, so let's say from a string to nothing. So let's say then you change from nothing to int. So you can basically convert from a string to an int, or from any type A to any type B. And so how is this, why is this happening? Well, the way this is working is that in some sense, we're doing it in a few steps to fool the type checker, but this value P has a type A where the member L has bad bounds. So the lower bound is any, and the upper bound is nothing. And because we're just setting it to null, we don't actually have to show that we have a real object of this type. We're just bypassing that. And this is where and this is basically through these bad bounds, we are able to basically go from an S of any to a U of nothing, if you want. If you go back to this rule here. Okay, so let's see. So this was a little bit surprising, but not that surprising because it was known in Scala for quite a while that there are issues like this. What was more surprising is that when discussing this with Ross Tate, he was able to create a similar problem in Java. And Java doesn't even have path-dependent types, but it's kind of the same idea that you add constraints that don't make sense, and by using null, you bypass having any evidence for these constraints. So at the end, it's a very similar issue. And it is also surprising because Java has been theoretically studied much more, and it's a simpler system. But what happens here is when you put many features together, and each one of them is sound, it makes sense in isolation. When you put them together, the interactions mean that you can get some surprising behavior. Okay, so let's look at what happens in the context of Dot and of Scala. In Dot, these issues with these subtyping collapse meant that it was basically giving an argument for why Dot is sound very hard. And the reason is that once you have a lattice collapse and you can convert anything to anything, then that means that it's very hard to guarantee that if you have an object that type checks as having a certain method, you really want to be sure that in the runtime structure, when this object points to something that does have this method. But once you have lattice collapse, it's kind of hard to make that argument. Okay, so let's see what happens in Dot. So when you have a type member T, and you have a lower bound S and an upper bound U as types, then by transitivity, you're kind of admitting that S is a subtype of U. And so just by adding type member definitions, you might be potentially admitting some relationships that were not provable before. And in particular, what happens if the bounds are nonsensical? So this is what happened in the example. We had the type T where the lower bound was top or any, and the upper bound was bottom or nothing. And then that means that we can really just collapse from an arbitrary type S to an arbitrary type T. So we have to be really careful about these bad bounds. And so one question is, can we exclude them statically? And because we want to also have intersection types, it's not really possible. Just if you look at this type, then in some sense it means that you can kind of choose if you want to have a bottom or top as the upper bound or lower bound. I mean, one way to think about it is that the lower bound takes the union and the upper bound takes the intersection. So here you would really go from, just by having this thing, it would be kind of similar to having a lower bound of top and an upper bound of bottom. So it would also collapse. And then maybe you can do it by verifying all intersections in the program. That's also not possible because as types get more precise, you also have problems. Just to give an intuition on this, before I get to these rules, I just wanted to give a small example with animals. So if you have an animal that has a type member food, and then you have a lion where food is meat and a cow where food is grass, then what happens is, like, you might want to share a byte between two animals, and let's just think of it as taking the intersection. But basically, it's in some sense, you don't know if you have two unknown animals, you don't really know until you have the most precise type of these animals whether they can share a byte or not. So if you have two unknown animals, they might just be both lion and they could share a byte, but if one is a lion and one is a cow, then maybe they have incompatible meals. And so in this example, what we can do is basically kind of make this this intersection of these two of these two food have bad bounds only when we have the full precise information about one being a lion and one being a cow. And so what really happens is that we have this tension between these two properties that are nice to have. So this one is just transitivity, which says that, you know, if S is a subtype of T and T is a subtype of U, then you would expect that S is a subtype of U. And this one is narrowing, which just means that if you prove something given some assumption, so the assumption that lambda is an animal, then it should still hold when you have more information. As in, if you then find out that lambda is a lion, it shouldn't invalidate anything you've already proven. Okay, so how did we reconcile this? Before I briefly get there, I just want to give another example of an issue. So this is this tension between type abstraction and type preservation. And the way to what happens is here we have this trait brand, which has a type hidden, which is completely abstract. But then we have an actual implementation where type hidden is equal to int, but here we are upcasting to brand. So we don't really know we don't know what we don't know that brand.hidden is actually int here, this brand. We don't know that. And so what happens is that as you compute in your system, you might start in a program which is completely okay, and then following the implementations of methods, you know that brand.pack is just here the identity function, so you know that you can replace this by 7. But now this program doesn't type check as it is. So as you're taking steps in your program, or you can think of as you're doing optimizations, suddenly your program doesn't type check anymore. So this was also something that we needed to resolve. And the main technical breakthrough, which I won't go into too many details, but it was to kind of have this distinction between concrete and abstract variables. So when you start the program, I mean, everything is abstract, but as you're computing, brand will be something that will be some object in the store, and then you have some very precise information about it. So in the proof, we do exploit that. And the way we do it is by basically, in these rules that I showed you, if we have an actual object that points to the store, we use the precise information we have about how the type member is implemented. Okay. So a good proof is one that makes us wiser. That's a quote by a mathematician, Yuri Manin. So what did we learn in this journey to prove, to design Dot and prove it sound? So, I mean, of course, I had many collaborators, starting with Martin Odersky and then Adrian Moore, Thierry Krumpf, Samuel Gritter, and Sandro Stucchi. And, you know, it was a lot of ups and downs, using many different tools and techniques. And I think it became interesting once we had a core design where we could really say, okay, this is even much nicer than what we started with in the vision, in terms of like being more uniform and at the same time being able to prove itself. And so what mattered at the end for proving soundness, I think, is also what, in some sense, what makes the calculus sound is also what makes it nice in terms of being able to reason about it. So in particular, really embracing subsumption and making sure that you never break these sort of monotonicity rules. One thing that is relevant for Scala is that recursion is really tricky. So in the calculus, we always check if things have objects must have good bounds, and we just check this syntactically. And in Scala, this is not possible because there's a lot of things that come in, including inheritance. And so you might inherit your bounds and things like this, and that makes it much trickier to check that cycles don't induce paradoxes. And I don't think, I mean, there's a lot of ad hoc checks for this, but I think there would be more work to do to ensure that there's a sound and principled design to avoiding these paradoxes. And so the impact on practice. So in the context of Dotty, the core type system based on Dot has simplified the type checker. Most of the things can desugar into this, and maybe the only thing that has to be treated as an extension is higher-kinded type. There's also some potential to lift ad hoc restrictions. So in particular, recursive structural types are more powerful in Dot than in Scala, but this is with the caveat that in Dot we don't have to deal with inheritance of objects, of implementation objects. And finally, characterizing soundness issues. So now we have a much better idea for why these, for when we would have issues with these path-dependent types in general. And there is, we do have the principle that every prefix P of a type selection must be a computable value. So this is why we don't want to, this is why one has to be careful with null values or lazy paths and so on. Okay, and so the delta between Scala and Dot, so as I said a few times, higher-kinded types. Of course, Scala also has richer types like singleton and others, and I mean, some we could try to model through encodings, and other might require extensions. Kind of studying maybe these orthogonal code-sharing mechanisms like inheritance and mixins. And in general, richer paths. So Scala has in Dot, paths are only variables, but this can be extended to chains of immutable field selections. And maybe in the theory, you could go even further by having, say, term lambdas in paths if you could show good properties about them. And just to show one final example of why things are trickier in Scala, this actually is a runtime cast exception in the Scala compiler, but Dotty catches it for some reason. I don't think there's any principled reason why Dotty works on this one and not Scala, but here it's just a little tricky to detect that these bounds are contradictory because they're mutually recursive. And so you get a similar issue as before. So if you're interested in this, in like diving a little bit more on the theoretical side, I would suggest this paper, The Essence of Dependent Object Type, that was published last year at Vadlerfest. It's a fairly accessible paper, yeah. So this is what I would consider next. Yeah. Thank you. Any questions? Yeah.
So, did the journey begin with finding that unsoundness?
Yeah, good question. So for me, the journey began by Martin giving me like, hey, this is like some design, like this vision of the calculus I want, and I found sort of like examples like this that were unsound in the calculus, but they not every time they would translate into unsoundness in Scala. They could just be like kind of yeah, just the calculus design was unsound. So for me, it was like almost a habit to then always try to find ways of breaking the soundness. The particular example with the null, what happened there was that I was presenting the results at a working group on language design, and Ross Tate asked, so what would happen if you add null into your system? So here, if we look here in our syntax, we don't have null, right? We only have these objects. And I told him, well, clearly it would not be good, because then you could have some object with bad bounds and via null, and that would be bad. So then immediately he was like, oh, so let's break Scala. I was like, and because Scala has a few ad hoc checks, it took us, like maybe 20 minutes to find a way around them. And yeah. But,
I guess like what I'm interested in is if this wasn't a motivator, but if it was, like how much of weird stuff in Scala's current type checker would be solved if you just didn't allow null? Because right here, like the null allows you to provide evidence for something that doesn't have it.
Yes, I think that's a good question. So I think it's in some sense it's like for an arbitrary type where you don't care whether you have a witness for that type or not. If you knew that like null was avoidable, then it would be fine, right? I mean, here you could rely on this a.l being okay if you've reached that point, for example. So for this particular thing, maybe it would be fine. I think in the case of Scala, we could prevent this particular issue by having null be explicit by default. So basically, changing to everything has to have an explicit union null to be able to use it. On the other hand, what's trickier in Scala and where Dot doesn't help so much is for examples like this, because this you wouldn't be able to write in Dot just because it's like, in some sense, you're constructing this object But in the calculus, we only really allow you to construct objects with type members as aliases. So syntactically, we're sure that they're going to be fine. But in Scala, you have to allow more things because of inheritance. And so this is yeah. So even if we solve the null issue, there would be other things to worry about.
Thanks.
Any other questions? Yeah?
So Dot doesn't have higher panda types, but you can simulate them using existentialists, is that?
No, I think it's so Martin and colleagues from EPFL have a paper at Scala at the Scala Symposium about trying to encode higher kinded types into Dot, or at least the core system used in Dotty, and it's really problematic because of these things where you kind of lose the type member structure. So I mean, basically, I could say, okay, I'll represent T as a type member, but now here, when I'm doing rep of T equals string, I kind of lost. I mean, I just have a string now. I don't have a type member anymore. So it's hard to say how you can maintain the correct relationships. So these two examples are tricky, and in general, it seems like you need to have some function at the type level to be able to do that faithfully. And there's, I think now, I mean, I'm not really 100% sure what is the latest thing, but probably Martin just now has an extension for that. In terms of like the theory, there could be many ways to go about it. So one would be like really just to try to add these typed lambdas, so to speak, to represent this. Or another way would be to maybe, if you extend the language of paths, maybe there would be ways then to encode these sorts of computation. If you allowed some sort of like computation in your paths that you knew would be normalizing and things like this. But that sounds even like a more like unconventional way of doing it. Oh yeah, and I should mention one idea for an encoding was to say that you might have some way to represent a function type by having, say, an in type member and then an out type member, and maybe being able to do computations, but somehow it doesn't work that well. So, any other questions? Yeah, yeah.
Since the background issue, would it be still problematic in a consistent language like Go or Agda or something like that?
Mm-hmm.
Is it specific to Scala, or is it more theoretical thing?
Which issue? Sorry.
I mean, the background issue.
Yeah. Okay. Yeah. That's a good point. No, so I mean, so people from these communities have told me that they've seen similar things. I mean, especially with this issue. So like I mean, this is not particularly related to bad bound, but this type abstraction via type reservation in a dependent type setting that might come up because you make some assumptions, but somehow like the assumptions are not all that coherent in terms of like covering the whole space. So I don't know, if you have some equality assumptions, how do you make sure that as your program progresses, you can still have them? So I mean, but in terms of specifically the bad bounds, I think in dependent types theory that translates to basically you have a context where your assumptions are contradictory, and so that may or may not be problematic. But yeah, basically just think of it as in here we tolerate bad bounds if it's only saying, well, we have a type that might have bad bound, and then we can have it as a parameter type. But basically that means that we will never be able to call this function if things are done correctly, because we'll never be able to create an object that has this type. And so in like the dependent type theory, you also have these things where at the end what you end up with is you're adding all these assumptions to your context, and maybe they're not consistent, and then how are you still able to carry your logic given that? So this is how it would show up.
Okay, but in Scala we could build like unsafe values
Mhm.
using general recursion, or are you using no? So in language, I mean, total language show recurrence. So is it the problem solved in different type languages? Or I wonder if how much does that Scala or languages in general?
Yeah, okay, I see what you mean. So I do think that if you start with a system where your values are like I mean basically where the the dependent terms are always normalizing and always good values, then maybe you have less of these issues. But I mean I did find some connections with like work going on, say in Haskell, for example, to add dependent types. I guess it's kind of coming similarly than like it's coming from a similar angle as Scala, where you have an existing language with existing features, and it's like how can you add a little bit of dependent types, right? Then you might run into similar issues. But yeah, but you're right. I think so. I've seen some problems that were similar in the dependent types words, but maybe they were not exactly about the bad bounds. But it's mostly about trying to maintain a coherent logic as you step through your program. Maybe we can discuss it offline. All right, looks like we're out of time, so thank you, and enjoy the break.